Good morning, good afternoon, or good night, depending from where you are listening to me. I would like to discuss first, before the lecture, some prerequisites you should have to follow my presentation. And that will be a base course. These are books that I have written, and that will be a book on physical chemistry, one semester, basic physical chemistry, thermodynamics, basic quantum chemistry, a 2-semester course. And the second edition of this book is here. So you should have also, you must have a basic knowledge of statistical thermodynamics. And I have another book on numerical methods in quantum chemistry, and also a book on history of chemistry, the visit of Marie Curie to Brazil, and the book was translated into Polish. In summary, the prerequisite you should have to follow the lecture is basic thermodynamics and basic statistical thermodynamics. Of course, it's also desirable if you have some knowledge of quantum chemistry. I'm going to talk now about the radial distribution function. That's a kind of correlation function. And this will be introduced in a didactical way in this chapter. And later on, we are going to see it in a more rigorous way by studying the Ornstein-Zernike equation. We want to describe liquids, and you probably realized that is a not very simple task. Liquids do not have the order of a solid, neither the disorder of a gas. So it's something in between, and the correct way to treat liquids is not through the virial expansion, as you may realize. In the last chapter, we handle hard sphere potential to calculate B3 and B4, but you can imagine if you have a real potential, not even with a central field symmetry, and you have to calculate the virial coefficients. Therefore, another strategy has to be adopted, and this is another strategy is by using the correlations function. G of R is will be denoted by the radial distribution function, and it describes the number of neighbors around a point, on average, of course. And let's give a very simple example. Suppose a solid in a BCC configuration. The first shell has 12 neighbors. But if you warm up the solid, this number of neighbors will probably decrease, let's say 8. And G of R will describe this neighborhood, and it can be used in gas, solid, and liquid. So it represents a general strategy to solid, liquids, and gas. If rho of R is the mean density at a distance R from some point, I can define initially the radial distribution function as a probability, which is equal to the density at R over the total density. And if I'm assuming a spherical symmetry, as it's going to be done here, I'm going to deal with central field potential. I can rearrange this equation to that, where this is it's implicit in this expression, the spherical symmetry. Rearrange again, I will arrive that the number of particles at a certain point equals to this integral. So you can already see that how important is the radial distribution function, since it can give me the number of particles in each shell. To make an analogy with gases, since you have studied gas before, up to the second virial coefficient. Let's consider a system that has no potential energy function. If the system is ideal, this will be the distribution of particles. It will be uniform. But if there is a potential in the system, you have to take into account the Boltzmann factor. And this probability has to be modified by that, where I change the number of particles to volume as well. Rearrange again and make the same manipulation I did here. I will arrive that the number of particles in this case for gas is going to be equal to that. Comparing these two equations, this one with this one, I can conclude that the radial distribution function gas is just the Boltzmann factor. And you are going to remember the discussion on hard sphere that we have done before on the Mayer function and the Boltzmann factor, as in the last chapter. Again, the analogy can be continued, and we have obtained that for gases, and you may conclude that it has to be modified to that, and the total energy has to be given by the equation 12. In conclusion, if you have the radial distribution function, you have all the thermodynamics quantities, like equation of state, free energy, internal energy, and so on. I would like to discuss now a one-dimensional model that's very useful to introduce a concept about the radial distribution function, which is given by this expression. This is a one model of hard sphere, and sometimes it's also called the hard rod model. It's important to mention that this expression is also a solution of Ornstein-Zernike equation, but it was not done using the first time. It was not obtained by using Ornstein-Zernike equation. It was obtained by using Randall-Walk in 1927 by Zernike-Prins. So they obtained an equation that was later modified by Kirkwood and the collaborators, and a lot of people work with this model. Hirschfeld and Maria Mayer, and also Tonks in 34, 36, but this final expression is due to Kirkwood. Sometimes it's called the Tonks model as well. But what is this unidimensional, one-dimensional model, the hard rod model, the Tonks model? It's basically a Zernike model, of course. It is basically a random walk around some fixed points. You see, we can see here the Poisson distribution. So it's Poisson distribution at one point, another, and so on. So you have now to explore this expression. You can construct a very simple program on that, and the next step now is to construct a code to explore this expression. And we have run it for density equals 0.8, and the result is here. You see the radial distribution function for hard sphere for the density equals 0.8. And this is the result. You have several shells. The importance of each shell decreases with the distance. And for density equals 0.8, the spacing is about the same as the diameter, characterizing the solid phase. But you have to run this code for the density equals 0.1, to see that it's going to appear only one maximum, only one peak in the radial distribution function characterizing the gas phase. In the problems, I ask you to modify this expression to a neat equation. It's given by that. That is the code to reproduce that figure and the others that you want, right? And that's the equation that I advise you to run other system. It's important to note that the radial distribution function for hard sphere will not depend on temperature, of course, because they are hard sphere. Thank you very much. Everyone that teaches probably has gone through this experience. After you give a lecture, you arrive at your office and think, I could have talked more about that subject. And that is what happened to me. So I'm going to complement the lecture by saying that this bullet here are classical dynamics calculation in one dimension for density equals 0.8. What I want to emphasize is that the model is correct because the calculation was done also, was performed also was performed also in 1978. It's a classical dynamics in one dimension, actually something that we teach in a classical dynamics course. That's a classical dynamics result. And you see that the model is correct for the assumption it assumes. I also felt guilty not to have run that code. Let's do it now. Let's put 0.8 as in the lecture. That's the graph. You see it's the same. 1, 2, 3 peaks, 4 peaks in the total. Let's decrease the density to see what happens. Let's try 0.6. Let's see if you keep the 4 peaks. 1, 2, 3, let's say 3. As I said, you are decreasing the density. You are reaching the gas state. And let's put 0.4. 1, 2 basically. Let's put 0.2. That's it. I hope I have finished the lecture now. Thank you very much.